form of f of n, t of n is theta of f of n. Now let's look at let's try to prove this for a more general form of f of n, where we don't assume that f of n is exactly of this form, but it's generally known to be big omega of n to the power log of a to the base b plus epsilon. So there could be some log terms in f of n, in the expression for f of n, in addition to a power of n that is larger than log of a to the base b. So how would we argue there that we're going to get a decreasing geometric series? Well, it's not clear that we'll be able to do that, at least in an easy way, because this series has the form f of n plus a times f of n by b plus a square times f of n by b square, and so on. And by assuming that f of n had a particular form, which was the some power of n, we were able to substitute that power of n throughout and show that the common ratio will be less than 1. But in general, when f has other terms in addition to that power of n, if it has log terms or other kinds of functions embedded within the expression for it, it's going to be harder to argue that this should necessarily be a decreasing geometric series. So we're going to make one more assumption. We're directly going to assume that a times f of n by b is going to be smaller than f of n by at least by some fraction. And this is true for every consecutive pairs of terms. So if you look at the statement for master theorem in the book, you'll find that case 3 is, it doesn't just assume that f of n is big omega of n to the power log of a plus epsilon, but it also assumes that the common ratio in the series, in the summation, is less than 1. More specifically, we are going to assume that a times f of n by b is going to be less than f of n. Not just that, it needs to be some fraction of f of n. Like, we don't want to have a decreasing arithmetic series. We want a decreasing geometric series. So we are going to assume that this second term is less than or equal to the first term by at least some fraction c. C is a number between 0 and 1. Some number between 0 and 1. So if this condition is true, that means the ratio of the second term and the first term is less than 1. The c is less than 1. So if we take f of n here in the denominator, the ratio of these two terms will be less than 1. And if we assume this for all n that is sufficiently large, then we can actually argue that for every consecutive pair of terms, the ratio of the term to the right to the term to the left will be less than 1. In fact, it will be less than or equal to this constant c. How do we show that? Suppose we replace n by b on both sides. Okay, I'm going to substitute n by b. So this is the assumption we are making, and I'm saying that with this assumption we can argue that we're going to get a decreasing geometric series. So let's substitute n by b, and we'll get a times f of n by b square is less than or equal to c times f of n by b. In general, we could substitute n by b to the power I, and we would get a times f of n by b to the power I, b to the power I plus 1 is less than or equal to c times f of n by b to the power I. So we can rewrite these inequalities as f of n by b is less than or equal to c by a times f of n. C is some number between 0 and 1, and we know that a is also a number greater than or equal to 1, because a is the number of subproblems into which the original problem is divided, which must be at least greater than or equal to 1. Now from this second inequality we get f of n by b square is less than or equal to c by a times f of n by b. But we know that f of n by b in turn is less than or equal to c by a times f of n. So if we substitute c by a times f of n in place of f of n by b, we are going to get something that is even larger. So let's do that. Let's substitute c by a times f of n. And what we get is f of n by b square is less than or equal to c by a squared times f of n. We can continue extending this result to prove in general that f of n by b to the power I will be less than or equal to c by a to the power I multiplied by f of n. Right? Because, so if you take f of n by b cube, for example, f of n by b cube will be less than or equal to c by a times f of n by b square. Right? If we put I equal to 2 here, f of n by b cube will be less than or equal to c by a times f of n by b square. F of n by b square is known to be less than or equal to c by a square times f of n. So if we replace f of n by b square by the right hand side, we'll get f of n by b cube is less than or equal to c by a cube times f of n. And in general, we can argue that f of n by b to the power I is less than or equal to c by a to the power I times f of n. Now the advantage of this result is that we can go back and substitute f of n by b to the power I by the right hand side of this inequality. And by doing that, what will happen is that we will get f of n, which we'll be able to pull out of this summation. Moreover, we'll get c to the power I divided by a to the power I, and this a to the power I will cancel with the a to the power I in the numerator. So effectively we'll be left with only c to the power I in the summation. Let's do that. Let's replace f of n by b to the power I with the right hand side of the inequality, since we are getting something larger, we'll say that T of n is less than or equal to the right hand side after the substitution, which will be a to the power I multiplied by the right hand side of this inequality, which is c by a to the power I times f of n. So we can pull f of n out of this summation because it's independent of I. So this is f of n multiplied by a to the power I times c to the power I divided by a to the power I. So these two cancel out again, and we get this geometric series c to the power I, which is a decreasing geometric series. Why? Because the value of c, which is the common ratio here, is less than 1. So this is in fact an assumption that we are making in case 3. So we are not only assuming that f of n is polynomially larger than n to the power log of a to the base b, we are assuming also that this inequality holds for all values of n sufficiently large. For very small values of n, it doesn't matter if this doesn't hold, because there'll be some constant terms and they won't affect the overall asymptotic complexity of T of n. So in general, this will be true for the examples that we take, because we just showed a few pages ago that if f of n exactly has this form, then the common ratio is provably less than 1 without needing any more assumptions. And in general, the algorithms that we look at for divide and conquer will be such that f of n will be some power of n. We won't usually have complicated terms like n cube log n and so on. F of n, remember, is the time required to combine the results of the subproblems, and they will usually be some powers of n. So if it's a power of n, we have exactly proven that the common ratio is going to be less than 1, and it's going to be this fixed constant 1 by b to the power epsilon, in which case T of n is something we prove to be in big O of f of n. Now we are trying to do it in general, and in fact we have assumed something more in order to help us with that proof. We have assumed that this inequality holds. That is, for all values of n sufficiently large, a times f of n by b will be some fraction of f of n. By making this assumption, we get a geometrically decreasing progression as we look at successive terms. And by getting a geometrically decreasing progression, this series becomes a decreasing geometric series, which we can upper bound. Again, using the same strategy, we can extend the number of terms here to infinity and say that this series f of n multiplied by the summation of I equal to 0 to h minus 1 of c to the power I is less than or equal to, we can simply extend the upper limit to infinity, make it an infinite series, and by doing so, we can use a simpler formula to say that this summation is 1 divided by 1 minus c. Again, we are using the formula where the summation of an infinite geometric series with a common ratio less than 1 is the first term divided by 1 minus the common ratio. This means that T of n is less than or equal to n to the power log of a base b times t of 1 plus 1 by 1 minus c times f of n. Now again, we can prove that this in turn will be less than, say, 2 by 1 minus c times f of n. Because f of n is polynomially larger than this power of n. So if we increase the constant coefficient, we are going to get a function that is larger than the left hand side. We can prove this by taking this term on the right hand side. So this will be 2 by 1 minus c minus 1 by 1 minus c times f of n, which will be 1 by 1 minus c times f of n. And this is greater than or equal to this term, which should be easy to prove since f of n is polynomially larger than n to the power log of a base b. So t of n is bounded from above by some constant multiple of f of n. And so t of n is in big O of f of n. Since we have already proven that t of n is in big omega of f of n, we can conclude that t of n is theta of f of n. Now, since we made this additional assumption, when we encounter recurrence relations where case 3 appears to be holding, that is, suppose we are given a recurrence relation for which f of n turns out to be polynomially larger than n to the power log of a base b. That's not sufficient to apply case 3. We also need to verify that this assumption holds. But things are easier for us since we have also proven that if f of n had the specific form of some power of n, right, if f of n was specifically of this form, then we prove that f of n is theta of, then we prove that t of n is theta of f of n without needing that additional assumption. Without needing this additional assumption, because we proved there that the common ratio will be less than 1. So, if you are given a recurrence relation where f of n is some power of n, then for us to apply case 3, it's sufficient to just show that f of n is polynomially larger than n to the power log of a to the base b. But if f of n has a more complicated form, something like this, then we also need to show that this assumption holds for that specific form of f of n, because it's only with this assumption that we were able to prove that t of n then will be theta of f of n. So if you want to use master theorem in that particular circumstance, you not only need to show that something like n cube times log of n is polynomially larger than n square, you also need to show that this inequality holds for that particular form of f of n. That is, a times f of n by b is less than or equal to c times f of n for some c less than 1. You need to show that there exists a number less than 1 for such that this inequality holds for all values of n that are large enough. And then you can use the result that master theorem provides, which is that t of n is theta of f of n. So we have looked at all the 3 cases of master theorem, and we are now going to take up examples and see that when we actually apply master theorem, we can quickly narrow down, we can quickly identify what the asymptotic complexity of t of n will be without needing to use the recursion tree method, without needing to build the full recursion tree. We can directly check which of the 3 cases of master theorem the recurrence corresponds to, and then use the corresponding result for T of n. So in this particular case, we have proven that T of n is theta of f of n. In this case, case 2, we showed that T of n is theta of either f of n times log n or n to the power log of a base b times log n. And in the first case, we showed that T of n is theta of n to the power log of a base b. This was case 1.